In this video, we discuss the convolution neural networks, one of the main architectures in deep neural networks for feed-forward case. In DNN, there are two main architectures. One is feed-forward DNN, and the other is recurrent neural networks. In the feed-forward, as we mentioned, convolution neural networks are the main architecture. And in this video, we'll focus on CNN. So CNN are designed specifically for image data. Image data are 2D or 3D data. Before CNN, the data fed to deep neural networks was in a vector form, in 1D. But for images, where the object recognition is a key application, we will find that it's feeding in the 2D, 3D image as a vector, which can be done. So if you write image X as an n cross n matrix, 2D image with Xij as the elements, you can vectorize it into, you can take row wise x11, x1n, x21, x2n, and so on, and make it a vector and feed into a deep neural network. But consider this. It's a simple black and white image with 0 and 1s. In this image, as you can see, there is a square pattern inside the image. We can actually look at it and observe it. If I vectorize this image into this vector and look at this vector, from this vector, we cannot make out, even as human beings, what kind of pattern there is. In particular, we cannot see that this vectorized form is an image containing a square vector. So if you do this, mathematically it is fine, but for the purpose of object recognition in images, vectorization has ruined actually very important information. It's the 2D spatial information that is important for object recognition, and this information gets lost in the vectorization. So therefore, it is important for the application of object recognition in images that we feed in to the neural network at 2D data as we see in the image directly. The other thing is that for object recognition in images, local information is very important. Within an image, there can be an object. For example, here, you look at this image, there are two chairs in this. To recognize that this is a chair, the information around this is important, not away in the image that you may be seeing. So therefore, local information is important in images, and the far off information is usually not relevant. So therefore, when in the neural network we are talking about the messages going from layer to layer, from let's say L-1 layer to L layer, we do not need to connect the output of all the elements or nodes in layer L-1 to all the nodes in layer L. So if we do that, we will have sparse connectivity of the nodes. So not all nodes in L- will be connected to L, and therefore the number of edges we can reduce in the network. This sparse connectivity in the neural networks has many advantages. There will be fewer edges for the same number of nodes and layers. Therefore, fewer weights will have to belong because each weight is associated to an edge. If there are fewer edges, there will be fewer weights to learn, which means that less training data is needed. Less training data is needed, and reduced computational load will be there for the training. So these are advantages of sparse connectivity. The other thing is, in the images, if there is an object, for example, if there is a chair here, and if instead of this place there is another chair, suppose the object is to differentiate between chairs and tables. So these chairs can be of different types, but both of them, for our purposes, may represent one class. Then whether the chair is in one corner or at another corner, the processing that is needed to recognize the image, the chair in the image, will be same, irrespective where its position is. Therefore, the connectivity pattern can be reused in the neural network at different nodes, and at the same time, computational processing can be similar at different places in the nodes. So these ideas, the weight sharing, the local information, as well as 2D information, these are used in the CNN architecture. And as a result, what has been found that for object recognition in images, CNN architecture turns out to be very, very useful. Okay, so here is the CNN architecture. At the input layer, we directly load 2D or 3D data. So let's consider a 2D image. So this may be a 2D image which can be loaded straight as such at the input. Then in CNN architecture, there is sequence of convolution and pooling layers. After the input layer, then convolution layer, then pooling layer, then convolution layer, and so on. So it is possible the architecture that is made is there is a alternate layers of convolution and pooling layers in this. After that, we have classification layer, fully connected classification. This may be multiple layers, typically 3 or 4 layers. It can be fully connected. It may also be sparsely connected, but the job of this is to do the recognition of the objects in the images. From there, the data enters to the output node, and in the output node, the output from the output node will give us the objects that we have found in the images. So, output node can give one image, one object in the image, or there can be multiple objects. And what it may do is, for whatever the number of classes are at the output, it may give the probabilities to different classes that may be there in the image. So if there are 10 classes, it can tell that the object in the image may have probability of one class at 0.1, another 0.6, another 0.3, and so on. So either you just take those probabilities, or you can then classify the object with the largest probability. So now let's explain the convolution layer and the pooling layer that we have talked about in the CNN. In the convolution layer, suppose L is a convolution layer, and we are talking about the jth node in layer L. and XLJ is the output of JF node at the layer L. This output is given by using the activation function at this node to the data that is coming from the previous layer. So this is the data output of the previous layer, XIL minus 1, ith node, output from the ith node at layer L minus 1. This will be multiplied by KIJL. So this is the kernel that we are going to define at layer L. And there is a bias, BLJ. This kernel elements are going to be multiplied by the outputs from the previous layer, and the outputs in the previous layer, we will not consider all outputs for node J at layer L, but only a subset of those nodes, which we are denoting as MJ. So this is the subset of nodes at layer L minus 1 whose output is used to feed into the jth node at layer L. The pooling layer, which may follow after each convolution layer, or there may be multiple convolution layers, and then there will be a pooling layer. So once the pooling layer comes, it reduces the number of nodes in the layer by, let's say, 1 by 4 to the number of nodes in the previous convolution layer, and it pools the outputs from the previous convolution layer into like from 4 nodes in the previous layer, the output is given to a single node in the pooling layer. So in this case, when we are talking about max pooling, these 4 nodes in the previous layer, convolution layer, might have outputs 1, 2, 4, 8. 1, 2, 4, 8. We take the maximum of this, and that goes here. Then from these 4 outputs of the previous layer, 5, 4, 3, 1, the maximum 5 goes into this node at the pooling layer. So this is how the different 4 outputs from the previous layer are made into a single output from max pool layer. The number of nodes also has reduced by 4. So this is max pooling. Instead of max pooling, you could have done average pooling. So in average pooling, instead of taking the maximum of these outputs as output here, you can take the average of these 1 plus 2 plus 4 plus 8 by 4. So that is another possibility. So we have now described the overall architecture of the CNN and after the input layer, which can be taking 2D or 3D data. There will be convolution layers and pooling layers. There can be multiple convolution layers and then one pooling layer, and then again multiple pooling layer, convolution layers, and then pooling layer, and so on. Or there can be a convolution layer, then pooling layer, convolution layer, and pooling layer alternately, multiple such layers. Then there is a classification 3-4 layers. After that, the output layer. As we go closer to the output layer, features become coarser because at the pooling layers, you are pulling the multiple outputs from the previous layer. Output of the CNN can identify an object, it can identify multiple objects in the image, or it can provide class probability for different classes as mentioned before. And how the class probability are given can be as follows. If at node I, the output, the sum of the inputs to output node I is Zi, then class probability of ith class will be Pi given by e raised to power z divided by summation of all z. So this is called softmax function. And after that, if one wants, one can give one class as the output, which is the highest probability class in this case. Now, training of the CNN. So we have explained the functioning of the CNN architecture, and of course, here also we have to do the training. In this case, the training will be done about the kernel parameters and the biases in the uh, convolution layer, as we explained, and also the weights that are there at other layers. These will be learned through a training data x1, y1 to xni, y1. Before you train, we can do some input preprocessing on the data, this training data. We can sample, we can scale this data so that it doesn't become too small or too large. We can subtract of the mean so that on the average, the mean of the sample is 0. We can also do what's called color jittering. If the images are colored, then what one can do is from the training sequence that we have x1 to xn, these are the images, these are colored images. We can even from these training data generate more images by changing the color in the actual training data and generate more images. So this is called color jittering. Doing that, we get more data and the resulting trained neural network becomes more robust. The training is done as before by gradient descent, stochastic gradient descent, or versions of it, for example, Adam and back propagation. Now, as we know, we have discussed earlier, when we are using back propagation, then there are issues in the training. Last video was explaining many of those issues. There can be vanishing gradient, they can be exploding gradient, and of course, data can go to local minima. So to take care of some of these issues, there are many tricks that have been suggested. One is how to initialize the weights where you start in the gradient descent kind of algorithm. The weights could be, initial weights could be from random sample from a normal distribution where the mean is 0 and the variance are 1 by NL, where NL is the number of nodes in layer L. So as the layer L is increasing from 1 to maximum towards the output, the variance may change, and the variance in particular layer depends on the number of nodes in that layer. If the layer has more nodes, then variance will be less. That's how we can start. Then there is dropout. In dropout, during the training, so it is only during the training, in the neural network, we can deactivate some of the nodes with probability P. What it means is its activation function, we can make it 0. The probability of doing that is small near the input layer. That means more nodes will be used in the training part, and it becomes around half near the output layer, because by then more and more input data would have been used in the training. Next thing you can do is gradient clipping. As we said, there is a problem of vanishing gradients and exploding gradients. These can be reduced, problems can be reduced if you clip the gradient on the positive side as well as negative side to maximum certain values. And one more thing that is used is what is called early stopping. When you are using SGD or even other Adam kind of versions, you do not iterate too long. You can stop the iterations a little early. This is called early stopping. So this helps in overfitting of the trained data. This has been observed empirically that doing this certainly does help. Okay, thank you very much. And we have finished with the CNN. In the next video, we'll be talking about the RNN architecture in the neural network. Thank you very much.